Good evening, Asimi is my name, and I want to do my presentation with respect to plastic deformation of I-beam. Plastic deformation is basically the condition whereby the shape of the I-beam does not return to the original shape when the applied force is removed. In that condition, we are going to be checking and verify the governing equation that might lead to that condition. These are the governing equation that I'm going to use, and when that happens, there is failure in engineering, so which means the I-beam phase, when there is any plastic deformation, it will not be able to do what is being designed for, what is being intended to do. These are the governing equation that I'm going to be checking. This is the bending stress, and this is the shear force, and this is the bending moment. This equation right here is the shear stress, and this parameter that you are seeing right here in this equation are from this shape of the I-beam, the thickness, the height, the breadth and height, and some other things like that. This equation is the safety factor equation. It is very important in engineering, as we do not want our system to fail. So in that case, we need to have safety factor, or the factor of safety, in order to make sure that the material works in a safe environment. And this is the deflection equation, as you are seeing right here. This is the slope of the deflection. This is the deflection itself, and this is the maximum deflections. So these are the equations that I'm going to be verifying in ANSYS with respect to my simulation, and see maybe my simulation is right or wrong. And this is my module. I want to use a cantilever beam, and the cantilever beam means that one end of the beam is going to be fixed and the other end is going to be free, and the length of my beam is going to be 500 millimeter, and there is going to be a force that is not constant. The force is going to vary, as you are seeing right here. So it's going to be a not constant force, or the pressure. This will be my 4 boundary condition that I'm going to use. My first boundary condition is, since that there will not be any deflection right here, when the deflection is equal to 0, the derivative of that deflection as well is going to be 0 as well. And right here, there is no bending moment and there is no shearing force. So those are my 4 boundary conditions that I have right here. What that means is that my analysis is going to be done within the assumption of this boundary condition that I have. This is the shape, or this is the dimension of my I-beam. We have different sizes of I-beam with respect to what you are intended to use it for. The application determines the size of the I-beam that you are going to use. So when you are designing, you need to have this at the back of your mind, that the parameter of the I-beam changes from one value to another. So you need to know the value that you are going to use, like the moment of inertia, elastic section modulus, the weight, the sectional area, thickness, some other things like that. We need to take those parameters into consideration when we are designing. So these are the parameters that I'm going to use with respect to the shape of my I-beam, and I got this information from this website right here, the American wide flange beam, and this is the site website. And this is the ANSYS environment. I created my I-beam, which is 500 millimeter long, and this is the shape of the I-beam that I created. So my 4 boundary condition is done here. This face is fixed, which means there is no deflection. The deflection is equal to 0, and the derivative of that deflection is equal to 0 as well. The other end that is free is there is no bending moment and there is no shearing force. And those are my 4 boundary conditions. Now I have my boundary condition, and this is my loading condition. So my loading condition is not going to be constant, and that's why I have a pressure that is not constant on this surface right here. The surface right here at this point is when the z is equal to 0, the pressure is equal to 0, and when z is equal to 500 millimeter, the pressure is going to be 4 megapascal, simply because the slope of the pressure is going to be 8 megapascal per meter. So this is my loading condition, and I did my loading condition in answers by choosing the option of the tabular form when I'm applying my pressure. So the tabular form gives me the option of varying my pressure at every point. So my pressure is not the same at every point. So the tabular form that I use, I created the value in a tabular form, and you can see this graph. This graph shows the value, or the graph of the slope of the pressure as z increases. When z is equal to 0, the pressure is equal to 0, and when z is equal to 500 millimeter, so the pressure is equal to 4 megapascals, you can see right here. And I did my analysis in 2 stepping. So what does that mean? Is that the first step is going to be the loading condition, the loading from 0 to 4 megapascal, and unloading will be the second stage, which is going to be from 4 megapascal to 0. So this is very, very important, because I have to do loading and unloading, before I can compare the shape before and after. So if I don't unload my system, I wouldn't have had the opportunity of comparing the shape, and I wouldn't have known maybe the shape is permanently deformed or not. So the loading condition is going to be the first stage, and the unloading condition is going to be the second stage, and that's why I have the 2 loading system here. And after the analysis, I solved the problem. I found out that my beam deformed plastically, and the condition that can make this happen is that the ultimate tensile stress of this analysis is much higher than the ultimate tensile strength of the material that I use, and the material that I use is structural steel, and the ultimate and the yield strength of the structural steel is 250 megapascal, which means the yield stress of this analysis is greater than 250, which is the yield strength of the structural steel. So in that case, the material fails, and we don't want that. This is permanently deformation. This is permanent deformation. This is failure, as I said, and we don't want that. So this shows the permanent deformation of the I-beam. This is the equivalent stress, as you can see, is 314.61 megapascal, which is greater than 250, which is the ultimate which is the yield strength of the structural steel, and that's why the material fails. These are the value at each point. You can see this is the maximum critical stress, and this is the minimal stress that we have. Each of these is the value at each of these points. This is the graph that I'm supposed to have at the end of the day, because this graph shows the permanent deformation graph, plastic deformation. From here to here is the plastic region of this graph, and from here to here, from here going like this is the first step, and from here to here is the second step. This is the loading condition, or this is the loading steps, and this from here to here is the unloading. And when I load my beam up to this place and I unload it, it has to come back here if there is no plastic deformation. But since I have plastic deformation, it cannot come back to the original shape, and that's why I know that my beam plastically deforms. This region right here is plastic deformation region, and this region right here is the elastic deformation region, and that shows that the beam plastically deformed simply because the yield stress greater than the yield strength of the material. I did another analysis with respect to the beam that has something like a support at the base, like this, like a square plate at the base, and I compared the same analysis with the one that does not have this first one right here, and I came to the conclusion from my analysis that the one that has the beam at the end like this, the equivalent stress is greater than the one that does not have, simply because you can see this is 362.26 megapascal, and the first one is 314 megapascal, approximate 314 megapascal. The reason is that this square plate had more edges to this system, and when we have more edges in this system, in the system like this, there will be more induced critical stress. And when we have more induced critical stress, there are chances of failing earlier than the one that does not have. So it is very important, it is very advisable not to add more edges to the system in order to avoid the being accumulating more critical stresses in the systems. That make more conclusion that the sharp edges contribute to the induced stresses in the systems, and we don't want that. Since I'm able to know this first concept, I did another analysis with respect to the one that has plate like this as well, but I use the modified tools to cancel the edges, to make sure that the edges I don't have sharp edges on the second analysis. And what I did is that I used fillet tools to cancel the sharp edges on this beam right here. This one I cancel the edges on this one, and this one I did not cancel the sharp edges on this one. Even the one that I did not cancel these sharp edges, and the one that I cancelled the sharp edges, there are differences again. There are differences due to the cancellation of the sharp edges in the I-beam. The difference, one of the major difference is that the one that I cancel the sharp edges, which is this one, has lesser equivalent stress than the one that I do not cancel the sharp edges. So that still tells us that the sharp edges are much more important. We don't need to have them. We have to cancel them out if actually we want to have a good less critical induced condition. So you can see this is 318 and this is 362. So the difference is very clear, and we don't want that. So we have to avoid the sharp edges in our system. And these are the results of my analysis. So the structural steel is a ductile material, and its atomic flowability during the tensile application is higher than that of the brittle. So it is very flow material. Its atomic flowability make it to be ductile. That's the one thing. From the cross sectional of the IB, the maximum tensile and compressive stress occur at optimal surface, while the maximum shear stress occur at the central. So the effect of the bending is easily noticeable than shearing force. So the bending, we can see the bending earlier than the time down the shearing force, simply because the bending effects occur at the ultimate surface of the beam, and there are relatively equal tensile and compressive stresses on the outer opposite surface of the beam, thereby projecting the bending effect and at the same time resilience the shear or impact force or impact effects. So that makes it easy as well to notice the bending effects. And the rectangular plates or the rectangular support at the fixed increases at the fixed end increases the critical stress and thus reduce the structural integrity due to more edges. So and the conclusion is that I-beam geometric selection is important for structural integrity, as it is affected by the ultimate tensile stress generated in the beam. So we have to bear in mind that the shape of the beam, which is the sharp edges, we take that into consideration when we are selecting the material, and the geometric selection, which is the moment of inertia, is very important, and the other parameter is very important when we are selecting the material. So the geometric modification, such as round fillets and some other things, we have to take care of that, so that we have the material that does not have the more edges. And factor of safety is very important as well, to prevent the failure, to prevent the structural failure. And poor design as well should be avoided in order to have appropriate dimension and some other things like that. So thank you very much. I really appreciate you for watching my video. Have a nice day. I thank